By the end of the 19th century, physicists had every reason to feel confident. Newton had given them a beautiful theory of mechanics, explaining how objects move and how gravity works. Maxwell had given them an equally elegant theory of electromagnetism, explaining light and all electrical phenomena. Both theories had been tested and confirmed. There was just one problem: they could not both be right. The trouble came from experiments with light. In the 1880s, Albert Michelson and others discovered something that made no sense in Newton's framework. Light always travels at the same speed, regardless of how fast its source is moving. If you throw a ball forward from a moving train, it goes faster than if you threw it from the ground. But light does not work that way. A beam of light from a stationary source and a beam from a speeding star travel at exactly the same velocity. This defied everything classical mechanics said about how motion should work. Older physicists struggled to make sense of this contradiction. George Fitzgerald and Hendrik Lorentz independently proposed an ingenious workaround. Perhaps measuring devices themselves were changing size and shape depending on their state of motion. If rulers shrink when they move and clocks slow down, you could explain why light always appears to travel at the same speed. It was a clever fix, but it felt like a patch rather than a real solution. Then in 1898, Henri Poincaré made a suggestion even more radical. Perhaps time itself was not absolute. Perhaps intervals of time, like intervals of length, depended on who was doing the measuring. The idea that time might be observer-dependent was genuinely revolutionary. Yet even Poincaré did not follow the thought to its conclusion. The pieces were all there, scattered across the minds of Europe's greatest physicists, but nobody had put them together into a coherent picture. The crisis deepened. Something had to give. The resolution came from an unlikely source. Albert Einstein was just a patent clerk in Bern, Switzerland, not a professor at a prestigious university. But he had been thinking about light since he was 16 years old when he asked himself a strange question: what would it look like to ride alongside a beam of light? It was a simple thought experiment, but it led him somewhere profound. If you could match the speed of light, Einstein realized, the light would appear frozen. You would see a stationary electromagnetic wave. But Maxwell's equations said this was impossible. Light had to move always, so Einstein made a radical move. He decided to trust the physics rather than his intuition about space and time. His solution was breathtakingly simple. He declared that the speed of light is the same for every observer, no matter how fast they are moving. This one assumption resolved all the contradictions that had plagued physics. But it came at a cost. For the speed of light to remain constant for everyone, something else had to give. That something was space and time themselves. Einstein showed that space and time are not fixed backgrounds against which events happen. They are flexible. They stretch and squeeze depending on how you move. When you move fast relative to someone else, your clock ticks slower than theirs. Your ruler measures shorter distances. Space and time literally convert into each other to keep light speed constant. Light, it turns out, is more fundamental than either space or time. This was Einstein's special theory of relativity, published in 1905. It shattered the old Newtonian picture of a rigid universe. Space and time were no longer absolute. They were relative, dependent on the observer. But Einstein had only addressed uniform motion observers, moving at constant speeds in straight lines. He had left out something enormous. He had left out gravity, and that would require an even more radical reconceptualization. Einstein had shaken the foundations of physics, but he had not quite finished the job. That final insight came from someone who knew him well. Hermann Minkowski had been Einstein's mathematics teacher at the Zurich Polytechnic, and he had not been particularly impressed by his student. Yet in 1908, Minkowski made a conceptual leap that would transform how we visualize reality itself. He realized that space and time were not separate entities to be combined through clever mathematics. They were components of a single four-dimensional fabric. In a famous lecture, Minkowski declared that space by itself and time by itself were doomed to fade away into mere shadows. Only a union of the two would preserve an independent reality. Einstein initially dismissed this four-dimensional interpretation as superfluous learnedness. He would change his mind soon enough, but his first reaction tells us something interesting. Even revolutionary thinkers can be conservative about ideas that push further than they are ready to go. Minkowski gave physicists a new way to visualize this four-dimensional reality. Picture a cone with its point at the present moment. The horizontal axes represent space, while the vertical axis represents time multiplied by the speed of light. Light itself defines the walls of this cone. A flash of light expands outward from the past, passes through the present at the origin, and continues into the future. Everything that can physically happen exists inside this cone. The region outside is forever inaccessible because reaching it would require traveling faster than light. Real objects trace paths through this structure called world lines. A person sitting still moves only through time, creating a vertical line. A person walking creates a slightly tilted line. A beam of light travels along the cone's edge itself. Every object, every event, every moment of your life can be mapped as a trajectory through this four-dimensional landscape. There is something haunting about this picture. The entire structure sits there static and complete. Your birth, your first steps, this moment right now, your eventual death, they all exist simultaneously in this four-dimensional block. History does not seem to happen, it seems to already be there waiting to be discovered, rather than unfolding moment by moment. This raised profound questions about determinism and free will. If the entire timeline of the universe exists as a completed structure, in what sense do we make choices? Are we moving through a pre-written script? Philosophers and physicists have wrestled with these questions ever since, and they remain unresolved today. After Minkowski revealed that space and time form a single four-dimensional fabric, Einstein faced a profound problem. His special theory of relativity had transformed our understanding of motion, light, and time, but it had nothing to say about gravity. Newton's law of universal gravitation had served science well for over 2 centuries. It described gravity as a force that acts instantaneously across any distance. The Earth pulls on the Moon, and the Moon pulls back with no delay whatsoever. But this posed an immediate contradiction with special relativity. Einstein had established that nothing, not even information, can travel faster than light, yet Newtonian gravity required instantaneous action across vast cosmic distances. The two theories simply could not coexist. This incompatibility launched Einstein on a decade-long quest. Between 1905 and 1915, he worked to understand how gravity could fit into his relativistic framework. The challenge was immense. Newton's equations worked beautifully for everyday situations, describing the motion of planets and the fall of apples with remarkable precision. But they worked only because the spacetime around ordinary masses is nearly flat. Newton's gravity was essentially an approximation valid in limited circumstances, but fundamentally incomplete. The deeper truths lay beyond Newton's reach. His theory could not explain why time passes more slowly near a massive object. It could not account for how light bends as it passes by the sun, and it offered no insight into the large-scale dynamics of the universe itself. Einstein needed a new conception of gravity, one that would respect the speed limit of light, while revealing the true nature of spacetime. What he discovered would change physics, forever. Einstein published his general theory of relativity in 1915, and it changed everything we thought we knew about gravity. The key insight was simple, yet profound. Gravity is not a force at all. Instead, it is a geometric property of spacetime itself. To visualize this, imagine a trampoline stretched tight. If you place a heavy bowling ball in the center, the fabric dips and curves under its weight. Now roll a marble around the edge. The marble does not travel in a straight line, it follows a curved path spiraling inward, not because something pulls it, but because the surface it travels on is bent. This is essentially what happens in spacetime. Massive objects like stars and planets press into the four-dimensional fabric of the universe, creating curvature. Other objects move through this curved spacetime and naturally follow bent paths. They are not being pulled by any force, they are simply going straight through a space that is no longer flat. The physicist John Wheeler captured this idea perfectly in his famous summary. Spacetime tells matter how to move, and matter tells spacetime how to curve. It is a beautiful reciprocal relationship. The math behind this insight lies in the Einstein field equations. These equations specify exactly how energy, momentum, and stress determine the shape of spacetime. They remain some of the most elegant and powerful equations in all of physics. Einstein's theory made predictions that Newton's physics could not account for. Time itself would run slower in stronger gravitational fields. This gravitational time dilation seemed strange, but experiments confirmed it. Atomic clocks at different altitudes tick at measurably different rates, just as Einstein predicted. Then there was gravitational lensing. Light passing near a massive object should bend as it follows the curves in spacetime. In 1919, during a total solar eclipse, astronomers observed starlight bending around the sun. The observation made Einstein an international celebrity. The theory also predicted that light climbing out of a gravitational well would lose energy, shifting toward the red end of the spectrum. This gravitational redshift was confirmed through precise measurements. Another prediction, the Shapiro time delay, showed that radio signals passing near the sun took slightly longer to travel, because they had to traverse curved spacetime. When scientists tested this using radar signals bounced off planets, the delays matched Einstein's equations perfectly. Perhaps the most dramatic prediction was the existence of singularities. These are regions where spacetime curves so severely that it tears. Today, we call these black holes. Nothing can escape them, not even light. For decades, black holes were theoretical curiosities. Now astronomers have photographed them and detected the gravitational waves produced when they collide. LIGO, the Laser Interferometer Gravitational Wave Observatory, directly observed these ripples in spacetime, confirming yet another prediction. General relativity also allowed scientists to extrapolate the universe's history backward. The equations predicted a beginning, a moment when everything expanded from an infinitely dense point. Scientists found the afterglow of this event, the cosmic microwave background radiation, confirming what we now call the Big Bang. Yet one mystery remains. General relativity describes gravity on cosmic scales, while quantum physics governs the subatomic world. These two theories refuse to play nicely together. Reconciling them stands as the great challenge for 21st century physics.